পঞ্চম দিনের ক্লাসে আমরা শুরু করব সেকেন্ড অর্ডার পার্শিয়াল ডিফারেনশিয়াল ইকুয়েশন নিয়ে। তো আমরা যদি ফিজিক্যালি আমাদের সামনে যে এক্সাম্পলসগুলো অ্যারাইজ করে সেগুলো একটু ভালো করে দেখি, তাহলে দেখব যে তার ম্যাক্সিমাম ক্ষেত্রেই কিন্তু আমরা সেকেন্ড অর্ডার পার্শিয়াল ডিফারেনশিয়াল ইকুয়েশন পাই। তো এবার সেকেন্ড অর্ডার পার্শিয়াল ডিফারেনশিয়াল ইকুয়েশন আমরা যদি লিখতে চাই, ধরনটা কেমন হবে? আগের বারে যেমন কি লিখছিলাম, যে আমি ধরছিলাম যে জেড, সেটাকে আমি বলছিলাম যে ইটস আ ফাংশন অফ এক্স ওয়াই। তো এক্ষেত্রেও একই রকমভাবে আমি কি করব, জেডকে আমরা ধরে নিচ্ছি ইটস আ ফাংশন অফ এক্স ওয়ান, এক্স টু, লাইক দিস, সো অন সো ফোর্থ, এরকম বেশ কিছু ভেরিয়েবলের সেটা ফাংশন। তাহলে আমার যদি এবার এক্স ওয়ান, এক্স টু, এক্স থ্রি, এক্স ফোর এরকম করে সমস্ত ইন্ডিপেন্ডেন্ট ভেরিয়েবলসগুলো থাকে এবং জেড একটি ডিপেন্ডেন্ট ভেরিয়েবল হয়, তাহলে এক্ষেত্রে আমি ডিফারেনশিয়াল ইকুয়েশনটি কীভাবে লিখব সেটা একবার দেখে নেব। সো দ্যাট উইল বি আ ফাংশন of all those independent variables, so x1, x2, so on, then z itself, then del z, del x1, del z, del x2, এরকম করে প্রত্যেকটি ইন্ডিপেন্ডেন্ট ভেরিয়েবলের জন্য পার্শিয়াল ডিফারেন্সিয়েশনসগুলো নেব। এরপর সেকেন্ড অর্ডার পার্শিয়াল ডিফারেনশিয়াল ইকুয়েশনসগুলো নিতে থাকবো। কীরকম? ডেল টু জেড, ডেল এক্স ওয়ান টু, ডেল টু জেড, ডেল এক্স টু টু, এটসেট্রা। এবং যেখানে এগুলোতে আমরা দেখো একটাই ইন্ডিপেন্ডেন্ট ভেরিয়েবলের রেসপেক্টে দুবার ডিফারেন্সিয়েট করলাম। এবার যদি আমি দুটো আলাদা ইন্ডিপেন্ডেন্ট ভেরিয়েবলের রেসপেক্টে ডিফারেন্সিয়েট করি, সো দিস del 2z, del x1, del x3, এরকমভাবে যত পসিবল কম্বিনেশনস তৈরি করা সম্ভব, লাইক del 2z, del x2, del x3 ইত্যাদি করে সব রকম পসিবল কম্বিনেশনস, অ্যান্ড দ্য হোল ফাংশন ইজ ইকুয়াল টু 0. দ্যাট ইজ দ্য জেনারেল ফরম্যাট অফ a second order partial differential equation when one dependent variable is there and other variables are independent on which that dependent variable is depending on. Now some examples. First example, এটা আমরা চারটে ভেরিয়েবলের ক্ষেত্রে নিই, অর্থাৎ স্পেসের তিনটি ভেরিয়েবল এবং একটি টেম্পোরাল ভেরিয়েবল নিলে আমরা দেখব এই যে উদাহরণটি, that suffix means here that is the partial differentiation. Now u is a function of x, y, z, t. Now del u del t is equal to some constant multiplied with double differentiation with respect to x, double differentiation with respect to y, and double differentiation with respect to z. This is the linear three-dimensional heat equation. Okay, now next example, similarly we are assuming that u is the function of x, y and z, then uxx plus uyy uzz is equal to 0. This is the Laplace equation in 3 dimensions. Now a similar run, যদি আমি t এর রেসপেক্টে ডিফারেন্সিয়েশনটাকে সেকেন্ড অর্ডার করে দিই, and uxx, uyy, uzz, and there should be a constant. And to say, just follow one thing: whenever we are taking a differentiation with a special variable, then we are doing, say, du dx, suppose, and the dimension of x is L, right? So whenever you are differentiating, the dimension will be the dimension of u and L inverse. And if you take a second order differentiation, then the dimension will be L minus 2. Now point is, if you differentiate the same thing with respect to t, then the differentiation, then that side's dimension will be this. Now as we know that the both sides dimension should be equal, right? And now how we will manage that part? That's why we will multiply a c square in this side. Now c is the speed of light, generally, whenever we take such a thing, or the speed of the wave which is propagating through the medium we are considering, then c's dimension is lt minus 1, and that will be adjusted, and this both sides dimension will be equal. So here we are taking this to be c square, the constant to be c square, and where c square means the wave, the speed of the wave which is propagating through the medium, and this equation is called linear three-dimensional wave equation. And the fourth example, say ut is equal to ux plus mu, a constant, multiplied with uxx. This is non-linear, right? Because some mu is multiplied with the u is multiplied with the differentiation of itself. So this is non-linear one-dimensional Burger equation. Okay, now in all those examples, follow that u is the independent variable taken. Now whenever a partial differential equation is considered, the order of the highest derivative occurring in that equation is the order of that partial differential equation. And suppose a second order partial differential equation means there will be a differentiation two times, or the highest order partial differentiation will be of second order. And now we generally do classify partial differential equation of second orders to solve them, because see, as many independent variables are incorporated, whenever you are working with all the differentiations, as we have seen before, there will be many terms, right? So it's better if we classify them, the equation, and then try to solve it and make some general formula or something like that. So whenever we want to classify, again I am not writing this cumbersome thing, a general formula I am writing. First we suppose that there is a function u, and the domain of u is this, and this is the set of points capital X, where every capital X a n tuple. If so, when n is n greater than 1, and then the partial differential equation's general formula will be written as ij is equal to 1 to n aij, this is the coefficient, uxi, that is the differentiation with respect to xi and differentiation with respect to xj as well. So it is the double differentiation part. And the second term, where the first order differentiations will be included, are written as bi uxi, and a part where the function of u itself is incorporated, another part is capital G, where parts which are not any differentiation of u, those parts are incorporated. Now as we have seen previously that there is a classification of quadratic equation, and whenever we were writing a quadratic equation as ax square plus bxy cy square dx plus ey plus f is equal to 0, we can classify this equation, this quadratic equation, as elliptic, parabolic or hyperbolic according as the sign of the discriminant, like b square minus 4ac. If this is negative, then we call it elliptic. If this is equal to 0, we call it parabolic, and if this is greater than 0, then we call it hyperbolic. Okay, so this is the convention for convention made for, I mean not a convention, actually this I mean that equation actually does represent such conic sections whenever this discriminant does have such signs. Now taking an analogy, we will compare with the this partial differential equation. So we write simply for two variables and two independent variables I mean, and one independent variable u, that is for if u is a function of uxy, then we write uxx, b uyy, c u bxy and uyy, then that will be in a series, a proper series, and dux euy fu is equal to 0. Say this is a given partial differential equation of order 2 in two independent variables, where this a, b, c, etc. may be the functions of x and y. Now for this, this actually ABC, these may be some functions of x and y, but for simplicity first we consider they are constants, and then we will check where, or rather take it like, suppose whenever you are going to solve a partial differential equation, actually you should have some x and y plane, and this is a u plane, and actually you are making this surfaces. U is a function of two variables, that's why U is a surface actually. Now say at a particular point x0 y0, you should have this a, b, c, etc. to be constant, right? So first we check at a particular point what is happening, okay, and so we are trying to find out the sign of the determinant, that is b at x0 y0 square minus 4 a x0 y0 into c x0 y0. So we will find the sign of this particular discriminant. Now whenever this is negative, we will call the concerned partial differential equation, this one, to be of a elliptical class, and when this is 0 is equal to 0, then we call this partial differential equation to be a parabolic one, and when this is greater than 0, we will call this partial differential equation of hyperbolic type. Now if you move in this space, this xy plane, then what? Then actually for any other point x1 and y1, say, you will again find this thing, and like that, if for the whole xy plane you get that b square minus 4ac is greater than 0, you will tell that this equation is hyperbolic for whole xy plane. Similarly, if it's equal to 0 or less than 0, you will say that this is parabolic or elliptical respectively for the whole xy plane. Okay, so this is the main funda. Now what we will do, knowing that these things are of such types, actually we will try to make the whole thing in some simple format. So just in the next lecture we will try to analyze how we can simplify this equation in its canonical form.